Hi guys, so let's see one small demonstration about electric dipole. Suppose if you take a charged balloon, so here the balloon is charging to the help of dog skin, so we can say dog fur, and now the balloon became charged. If you bring the charged balloon close to water, do you observe? The water is trying to attract the balloon. So let us understand why it is. This is because water molecule is an electric dipole. So dipole means you should have more than two charges and two oppositely charges. If you can see at here, the water molecule which attracts towards to the charged balloon. So if you bring close to the water, so this is a charged balloon, and if you can see the water stream is bending towards to the charged object. So this is because when we bring a charged object, sorry, so if this balloon is negatively charged and if water molecule is trying to attract that charged molecule, so now here the water molecule turned by itself. So before, so this is in this position, so this is the position of the water molecule. Now you just observe what is the position of the water molecule. So the position of the water molecule gets turned. So that is due to because of the effect of the electric field on this water molecule. So in simple words we can say, if an electric dipole is present in the electric field, if an electric dipole is present in an electric field, so there is a torque which acts on this dipole. Because of this torque, so the dipole starts to rotate within the electric field. You know that what is the meaning of torque? Torque means two oppositely forces will be acts on an object. So because of the two opposite forces, so the object should be twist. So same thing happens to this water molecule also, or to dipoles if they are present in an electric field. So that is today's math concept, torque acting on an electric dipole in an electric field. Let's recall what is electric dipole. Electric dipole consists two oppositely charged. Suppose if you take negatively charged and positively charged, so they are separated by a distance 2a is known as dipole length, but all together this stuff is we call as electric dipole. So this everything we call as electric dipole. So electric dipole consists of two oppositely charged and they are separated by a distance 2a. So this electric dipole having dipole moment, so that we represent with p bar. The dipole moment direction is from negative to positive charge. So that is the electric dipole moment direction. The electric dipole moment P we can write as P equal to the product of the charge times its distance or dipole length. So I can take either the magnitude of the charge as a q times dipole length equal to 2a. So this simply you can write p equal to 2qa is known as dipole moment. This dipole moment having the magnitude and its direction, if you can take the direction of the dipole moment, is along from negative to positive charge, that we can represent as p cap. So that is from negative to positive charge. Now, what are the units of the dipole moment? So, charge units are the coulomb and length units are the meter. So, you can take as coulomb meters are the SI unit of dipole moment. So, this is the background knowledge we have about the dipole. So, but today's concept, what happens if we keep electric dipole in an electric field? So this is the concept. Electric dipole in an uniform electric field. So we keep electric dipole in an uniform electric field. Let's see the concept. Torque on a dipole in a uniform electric field. Suppose this is a uniform electric field. So the electric field direction is along in this direction. So this is the direction of electric field. Suppose if I bring a dipole in this electric field. So I would like to draw a dipole just like this. So this is the electric dipole which I kept in this electric field with this inclined direction. So at here one charge and at here another charge. If I take this is negative charge and this will be positive charge. And the dipole length, so the dipole length we are using 2a. So this is the dipole length. Now we know that dipole moment only the dipole moment P equal to the product of the charge times dipole length 2a equal to 2qa, and dipole moment having the direction, so it's the direction along the P cap. So inwards you can write from minus q to plus q. So that is the direction of the dipole moment. Now this dipole is present in the electric field. So what happens if it is present in the electric field? So if the electric field is in this direction and in the electric field two charges are there. So this electric field will interact with the charges. So because of that interaction, force will be acts on these two charges, and we know that in which direction the force will be acts. Suppose since it is the electric field in this direction, if the positive charge is placed in electric field, the force on the positive charge is along in the same the direction of the electric field. So this is the force the direction which acts in the positive charge, and in the negative charge the force direction will be in this direction. So this we know by using convention we are writing, and we are showing the direction of the force at here. So if I can write force on positive charge, force on plus q, if you can write f suffix positive q, The relation between charge and the electric field equal to Q times E. And the force on negative charge which equal to F suffix minus Q equal to minus negative times electric field E. So what is the total force? Total force capital F equal to, if you can sum up these two, QE minus QE equal to 0. See this at here? Even though the total force equal to 0 on an dipole in an electric field, but still there is a force which is acting. That force causes the dipole to rotate. Again repeating, still even though the force acting on an dipole in an electric field is 0, but still the dipole is rotating in an electric field. So we can say the net translation force on a dipole in a uniform electric field is 0. The net force is 0. The net force is 0. But two equal and opposite forces act at different directions points of the dipole. Yeah, this is the key point. Two equal and opposite forces acts at different points on the dipole. So because of that, two different and opposite forces are acting. So because of that, a couple forms. So because of these situations, I can say they form a couple. Which exerts a force. So here couple is not what the couple you are thinking. In mechanics, couple is a force. So if it is like that, suppose if you take an object and if you apply a force in this direction and if you can apply a force in this direction, two forces acting oppositely. So because of that forces which are acting opposite in directions, so because of that forces, so what happens? A couple forms. Because of the couple, here the dipole starts to rotate. So that contributes to us, what is that? Torque. Now, what is the definition of a torque? Torque equal to force times perpendicular distance. Now we need to figure it out. What is the perpendicular distance? And we already knew that what is the force. So for that, in this figure, suppose if you make a perpendicular distance, I need to find what is the perpendicular distance. For that, we need to make, if you can make a triangle over there. Yeah. Now I need to find this perpendicular distance. So this is the distance, I need to find it out. This we need to figure it out. Now if you take this as the dipole moment P, which is making an angle theta, and this angle is already equal to 90 degrees. Now from figure you can write sin theta equal to perpendicular by hypotenuse. So here the perpendicular I need to find, but we know the what is the hypotenuse. So if we can write the sin theta at here, so we need to find it out what is the perpendicular distance, and the hypotenuse, it is nothing but dipole length. So I got it here perpendicular distance equal to 2a sin theta. So this is the perpendicular distance. So if I mention that at here the perpendicular distance equal to 2a sin theta. Now we can find the torque formula. Torque equal to force, Coulomb force QE times perpendicular distance equal to 2a sin theta. Tau equal to, if you can write it properly, 2QEA sin theta. And if you notice, in the place of 2Q times A, I can write as dipole moment. The dipole moment P equal to 2QA. So finally we can write tau equal to PE sin theta. So this is the torque relation in electric field, in an electric field. So the torque causes the dipole to rotate. Now what is the direction of this torque? If you can see properly at here, so the electric field is also having direction and dipole moment also having direction. So from the figure you can find it out that, if you can clearly notice at here the electric field direction, so this is the electric field direction, this is along in this direction, but the dipole moment direction is along in this direction. The resultant of that two, if you can guess that properly, now we can figure it out what is the torque direction. Or if you can think logically, tau equal to PE sin theta, which also I can write as P bar cross E bar. It means the cross product of two vectors. So we know that A bar cross B bar equal to AB sin theta. So this is the cross product of two vectors. So easily we can figure it out what is the torque directions. Now if these three vectors are mutually perpendicular, now it means if I show this is the electric field directions and this thumb is the dipole moment direction. Now the torque direction is along in this direction. So the torque is direction sensitive. So we need to find it out. The torque directions depends upon the dipole moment direction and electric field directions. Let us see a case. When is torque maximum, tau maximum, or when is tau minimum, or when will be tau 0? Yeah, since it's a force, it will be max and it will be min and it will be 0 also. So maximum case, if you can see sin theta, when the theta is maximum, so sine 90 degrees. If you can write tau max equal to P sine theta, if theta equal to 90 degrees, sine 90 value goes to 1, that implies sine 90 equal to 1. So that implies the tau equal to P. When the tau equal to minimum, so if you take the same formula P sine theta, if theta equal to 180 degrees, if 180 sine 180 degree equal to minus 1, which equal to minus P, and when the tau equal to 0, when the tau equal to 0, if you can take P sine theta, so if theta equal to 0 degree, so sine 0 equal to 0, now the tau value becomes as 0. So the torque is maximum, and the torque will be minimum, and the torque will be 0. So because of this interaction of the electric field with the dipole moment, since that both are the two vectors, the interaction of the two vector causes another vector coming to picture. So here another vector is torque. The torque causes the dipole to rotate in an electric field. So that's why the water stream is trying to lean towards to the balloon. So this is the concept of the torque acting in a dipole, torque acting on a dipole in an electric field.